Let's continue looking at our matrices. This time we are going to learn about how to find the inverse of matrices. Before we can learn how to find, we need to know what it is. So let me give you the definition of the inverse of matrices. I define A is an n by n square matrix. If there exists another n by n matrix, let's call it A inverse. It looks like A to the negative 1 power, but indeed it's A inverse, such that A times A inverse is equal to an identity matrix, and A inverse times A equal to an identity matrix. Let's remember, for the matrix multiplication, we don't have the commutative property, so it's very important to check A times A inverse and A inverse times A. If these two conditions are satisfied, then we call A inverse is the multiplicative inverse of the matrix A. Let me explain this, what the identity matrix is, if you have forgotten that from the last time we learned the matrix. So the IN is indicating an n by n square matrix with all the diagonal elements are ones and the other elements, they are all zeros. This is the identity matrix. For instance, 2 by 2 identity matrix is 1, 0, 0, 1. Etc. Keep that in your mind that not all the matrices have inverse, okay? And if a matrix A has an inverse, then we call this matrix is invertible, or sometimes in some book we call that as non-singular. So otherwise, the matrix is called singular. And another fact is a non-square matrix definitely don't have any inverse. Okay, now let's take a look at how to find the inverse of matrix. There are several methods to find the inverse of matrix. The one I want to share today is using the do you remember the Gauss-Jordan method? We are going to replace a matrix on the left-hand side of the arithmetic matrix, and the right-hand side of the arithmetic matrix we are going to replace the corresponding identity matrix, which means if A matrix is n by n matrix, we are going to put a corresponding n by n identity matrix. Then you will perform several row operations, and to somehow I can say that unofficially we can say that move I to the left hand side of the arithmetic matrix, and the right hand side of the arithmetic matrix will be the inverse of our matrix. And also let's recall what are the row operations. The row operations including we can interchange the rows, and we can multiply a row by a non-zero constant, or we can add two rows together. So those are the row operations. Now let's take a look at an example how to find the inverse of a square matrix, and then how to check if this is the inverse we are looking for or not. you are given a square matrix. Let's work on a 3 by 3 matrix. -2, 4, -1, 0, -2, -3, -1, 2, 0. We are going to find A inverse if it exists. Remember, not all the square matrices have inverse. Okay. Well, we started with putting A on the left hand side of the elementary matrix and the corresponding identity matrix on the right hand side. So this elementary matrix will be a little bit look different from the system of linear equations. -2, 4, -1, 0, -2, -3, -1, 2, 0. This is the matrix A. And the corresponding 3 by 3 identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. At the end, we want to have this part to the left hand side, and whatever the result on the right hand side will be your inverse. Then we are going back to the diagonals, and for the identity matrix, we want this diagonal be ones, right? And then the other term will be 0. Well, I noticed something that the last row is have -1. Maybe it's easier to switch this one to 1. First step, I'm going to interchange row 1 and row 3. So the row is including the entire things, including the right hand side of the elementary matrix. Row 2 is the one remaining the same. Let me copy it down. And row 3 become row 1. So -1, 2, 0, 0, 0, 1. Row 1 become row 3. -2, 4, -1, 1, 0, 0. To make this number be 1, we can multiply the entire row by -1. So -1 times row 1. That will give us 1, -2, 0, 0, 0, -1. 0, -2, -3, 0, 1, 0. And this one will be -2, 4, -1, 1, 0, 0. Nothing changed in here. This number in here, in the diagonal, the first element is our pivot. We are going to use our pivot to clear the elements below the pivot be 0. Let's take a look. Well, in here only the row 3 have -2, row 2 have 0. We don't need to worry about the row 2. To clear this number, we need to use the pivot times 2. So we get 2, 2 plus -2, that is 0. So we have 2 times row 1 add into row 3 to replace row 3. Again, pivot is the tool, just like the hammer you're using. You're not going to change it, so you will keep the pivot row the same. And second row, I don't do anything, so let me copy it down. The third row is 2 times 1 is 2 minus 2 is 0. 2 times -2, -4. -4 plus 4, that's 0. 2 times 0 is 0, plus -1, that's -1. 2 times 0 is 0, plus 1, that's still 1. And similar, this is 0. 2 times -1, that's -2 plus 0, -2. Okay, we walk down to the diagonals. So the next element in the diagonal is -2. We want to make the -2 be 1 as well. Alright. Well, the only thing we can do at this moment is divide the whole row by -2. So row 2 divided by -2. Keep in your mind that every time when you deal with the number like this, keep it as a fraction, don't round it as a decimal. Row 1 remain the same. Row 3 remain the same. Row 2, everything divided by -2, so that will be 1. That will be 3/2 and 0, -1/2 and 0. Okay, now this one become your pivot, and you're using that to clear the elements above and below. It seems like we only have the row 1 need to worry about. So we'll use row 2 multiplied by 2, add into row 1 to replace row 1. Okay, again, the pivot row is the one remain the same. And since we are not doing anything for the last row, so we copy it down as well. Alright, So 2 times 0 is 0 plus 1 still 1. 2 times 1 is 2 plus negative 2 is 0. And 2 times 3 half, that is 3 plus 0 is 3. And this one is 0. 2 times negative 1 half, that is negative 1 plus 0, that's negative 1. And 2 times 0 is 0 plus negative 1, that will give us negative 1. Continue working on the diagonals. Okay, the next element, which is the last element in your diagonal, is negative 1. We need to change that into 1 by using the row operation. And let's see, we can just multiply by negative 1 to change the sign. So row 3, we use that to multiply negative 1. And 1 and 2 still remain the same. So it's 1, 0, 3, 0, negative 1, negative 1, 0, 1, 3 half, 0, negative 1 half, 0, 0, 0 times negative 1, that's 1, that's negative 1. So basically just switch to sign. Alright, so this element become our pivot. And use this one to clear the elements above, which is the row 1 and row 2. Let's see, the row 1 is 3, so I need to have row 3 to get negative 3. So negative 3 times row 3 add into row 1 to replace the row 1. Again, the last row is your pivot row. Let's keep it. And the first row times, use the last one times negative 3, add into the first row. So 0 plus 1 still 1, 0 plus 0 still 0, negative 3 plus 3, that's 0, and negative 3 times negative 1, that's 3, 3 plus 0, that's 3, 3 times 0 is still 0, plus negative 1 is negative 1, negative 3 times 2 is negative 6, plus negative 1, that is negative 7. The next row, 3 half, right? So a little bit challenge, but we can do it. I know we don't like fraction, but we still need to do it. Make it as negative 3 half. So negative 3 half row 3 add into row 2 to replace row 2. Similarly, 0 plus 0 is 0, 0 plus 1, that's 1. 1 half times negative 3 half, that's negative 3 half, plus 3 half, that will give us 0. Negative 1 times negative 3 half, that will be positive 3 half plus 0, 3 half. Then this one is 0 plus negative 1 half, negative 1 half. And 2 times negative 3 half, that's negative 3, plus 0, that's negative 3. Okay, it seems like we have finished our mission, which is having the identity matrix on the left hand side, which is proposing the right hand side is our inverse. The reason I say this is a proposed solution, we have to check, always check the solution. Right? By checking if this is really your inverse, we need to use A times A inverse. Hopefully we can get into the identity matrix. Matrix A is negative 2, 4, negative 1, 0, negative 2, negative 3, negative 1, 2, 0. Times the proposed inverse. Okay, the proposed inverse is 3, negative 1, negative 7, 3 half, negative 1 half, negative 3, negative 1, 0, and 2. Okay. Remember how we multiply the matrices? Okay, this is 3 by 3, multiply 3 by 3, right? So your result will be 3 by 3 as well. So you have 3 rows and 3 columns. Okay. So each row and each column, the position, the row comes from the first element and the column coming from the second element. So for instance, this one will be using negative 2 times 3 plus 4 times 3 half plus negative 1 times negative 1. That's this element, first row, first column. That will give us negative 6 plus 6 plus 1, so that's 1. This is this element. Okay, moving to the next one. This one is first row, second column. So again, the row comes from the first element, first matrix. The column comes from the second matrix. And you can see this is negative 2 times negative 1 plus 4 times negative 1 half plus negative 1 times 0. and this is 2 minus 2 plus 0, that gets 0. Okay. If you carry these calculations along, you find out this is 0 and this is 0, 1, 0, 0, 0, 1, which is identity matrix. Yes, it's true for A times A inverse. Again, you have to check the second condition, which is A inverse times A, which is using 3, negative 1, negative 7, 3 half, negative 1 half, negative 3, negative 1, 0, 2, and multiply the matrix, negative 2, 4, negative 1, 0, negative 2, negative 3, negative 1, 2, 0. To carry out this multiplication similar to the one above, and eventually you find out, yes, we do get an identity matrix as a result, so that is true. Therefore, after you check both conditions, then you can draw a conclusion that the inverse is equals to 3, negative 1, negative 7, 3 half, negative 1 half, negative 3, negative 1, 0, 2. Alright, we are going to stop in here, and the next time we come back to see how we use the matrices inverse to find the solution of linear equations.